Thank you for inviting me here, and hopefully I can say something interesting. Yeah, so today I'm going to talk about these Poisson manifolds of strong compact type, and basically what I'll do is I'll go over the a construction of a few of these. So I'll start with introducing what these things are, and then yeah, go over this construction and yeah, see what we end up with. Right, so just a bit of introduction. So these Poisson manifolds of compact types are basically the Poisson counterpart of like Lie algebras of compact type in Lie theory. So the idea is you look at the infinitesimal object, which would be a Poisson manifold, and then you say it has a certain compactness type if the global counterpart, so symplectic groupoid, has this type of compactness. Now, in this case, there are, of course, multiple notions of compactness for groupoids. So you have properness if the anchor map is proper, source proper if the source map is proper, and then finally compact if the actual space of arrows is compact. And then, right, and just in the case of Lie algebras, you have like the distinction between taking any integration and taking the largest one. So in this case, the source one connected one. And then you get sort of 6 different types of compactness for Poisson manifolds. And just to fix the terminology, you would say, like, for any of these compactness types, you say that a Poisson manifold is of proper or source proper or compact type if there is a source connected Lie groupoid integrating it, having this property. And then you say it has strong proper, strong source proper, strong compact if the Weinstein groupoid, the one connected integration, the source one connected integration, has this property. And then, as you saw from the title, we're going to focus on the strongest one of these, so the Poisson manifolds of strong compact type in this case. Right, and I already told you basically what I'm going to go over is a construction of some examples, because it turns out that finding examples of these PMSCTs, the strongest type, is quite difficult. So in general, finding examples of Poisson manifolds of compact types is you can find interesting examples quite easily, really by just looking at your standard examples of like zero Poisson structures or linear or symplectic or whatever. You can find like criteria for these things to have a certain compactness type. But then basically the only like strong compact example that you get easily like this is that in the case of symplectic manifolds. If you have a compact symplectic manifold with finite fundamental group, this will always be a PMSCT. Basically because the Weinstein group in this case is just a fundamental groupoid, and under these assumptions, it will be compact. Right, and then if you want to find non-symplectic examples, it's quite hard to find these things, and there's really only one type found. Basically, even all the examples I will give today, even though there are many, they will basically all arise from the same construction. So this construction is originally due to Martinez-Torres. He constructed the first non-symplectic PMSCT. And this construction is heavily inspired by the solution to a different problem in symplectic geometry, which is about the existence of free symplectic circle actions on closed symplectic manifolds, which have contractible orbits. Then Kocik gave a construction of one of these things. And then it turns out that if you take the quotient by this action, you get a Poisson manifold, which is actually a PMSCT, which is non-symplectic. So it's going to have leaf space S1. And the crucial ingredient in this construction is our K3 surfaces. So there's a lot of like remarkable strong results relating to K3 surfaces, and using them you can construct this thing. So what Martinez-Torres did, he basically reformulated this construction like directly from the Poisson point of view. So giving general criteria for constructing PMSCTs using K3 surfaces. And then he gave this example of a PMSCT with leaf space S1. Basically, what we're going to do today is we're going to use this this setup to find more examples over 2 tori. Right. So I mean, there's a lot of course, interesting things about these PMCTs that I can't go over today. I'm not going to be able to do that justice at all. But just one thing that you can say about PMCTs in general is that the leaf space is always an integral affine orbifold. And in the examples that I already mentioned, I mean, the symplectic one, the leaf space is a point, so nothing going on there. But for S1, you just have the standard integral affine structure by looking at it as like R mod Z. And then it's not known whether any integral affine orbifold can appear as a PMSCT, right? I mean, you only basically found the point and a circle this so far. But then what you can say, and what I'll go over today, is that actually any strongly integral affine 2 torus does appear as the leaf space of a PMSCT. Or I should clarify then the terminology here. So strongly integral affine means it's integral affine, but you require the translational part to also be integral. Okay, so in general, those can be real, but you want them to also be integral. And then for all such 2 tori, you can construct a PMSCT with that torus as its leaf space. So that's basically what I'll go over. Yeah. And then, so the plan is basically to first give you a general idea of how you can construct PMSCTs. And then I'll go over how you can use K3 surfaces to actually apply this construction. Basically going to be a slight reformulation of this original result by Martinez-Torres, but yeah. Right, so basically the idea of constructing this PMSCT is by looking at 2 main properties that PMCTs have, and then sort of starting in a very simple setting, satisfying these two properties that it must have, and then sort of showing that if you work with this, you will actually end up with a PMSCT. So those 2 main results that we will use is, well, the first one I already mentioned. It's the fact that you have this integral affine structure on the leaf space of a PMCT. And then the second is the linear variation theorem. So this holds for any Poisson manifold of S proper type, so in particular for compact type. And this is basically like this basically says that if you look at the symplectic forms on the leaves of your manifold, your Poisson manifold, that it varies linearly in cohomology when you move between different leaves. Now, of course, making this precise is a bit of work, but in this case, you don't have to worry about that, because the way I'll set up this construction is it's very simple. It's really like a Dijkstraat-Heckman type formula like this. This is what you can think of. So just think of, because we will actually start with the Poisson manifold whose leaf space is just Rn, right? So then you can make this linear variation very explicit like this. So you have some integral classes, linearly independent integral classes Ci, and then you assume you have a formula like this, where omega v is the symplectic form on the leaf over v, right? So this is what you should keep in mind here. Right, so then, like I said, you're gonna sort of start in a very simple setup, assuming these 2 things, and then use this to obtain examples. Okay. So just to be a little bit more precise about this, so what you can do is you can start with, like I just said, you can start with a Poisson manifold over RQ. So by what I mean by that is you take a fiber bundle over RQ, where the fibers are the leaves of your Poisson manifold. So you're going to start with that, and then you're going to assume that you have compact well-connected leaves, and then you can and then you can just require this to hold, right? So we're just going to assume we have a Poisson manifold over RQ for which this linear variation holds. Okay. And then this Poisson manifold already will be strong as proper. Okay, so that's sort of what you immediately get. And now sort of the problem is you want it to be strong compact, right? So then you're gonna, in particular, you're gonna need this leaf space to be compact, right? And basically the way that we will do that is by taking a suitable quotient. So we're gonna quotient RQ by in such a way that we obtain a compact integral affine manifold as leaf space, okay? So how do you do that? Well, I'm gonna take a discrete subgroup of integral affine transformations. And then I assume that will act freely, properly, and co-compactly on RQ. Right. So this means that if we take the quotient, we get a compact integral affine manifold. Right. There's always an induced integral affine structure when you take a quotient like that. And then this is I mean, I'm writing everything down. It's easier said than done. You're going to assume that this action lifts to a Poisson action on this Poisson manifold. Okay. And then it turns out you can show that if you then take the quotient, you get a PMSCT whose leaf space is this RQ mod gamma that I talked about. Okay, so you can see also in this construction that you can basically like prescribe the integral affine structure on the leaf space, right? If you construct it in this way. Yeah, so like I said, this is easier said than done. I mean, this is fine, but actually finding the correct ingredients for this is the hard part, right? And like I said, only K3 surfaces so far have been found to really be able to apply this. Yeah. So yeah, so like I said, in this construction, there are some restrictions on like the candidate leaf that you would use. Basically, one very difficult thing is the fact that this action needs to lift, right? So because, so on the one hand, you want this action to preserve the fiber-wise symplectic form, but you also know that these forms satisfy this linear variation, right? So then basically you're gonna have to satisfy some equation with how you act and these CIs, right? There's gonna be some equations you can write down that you need to satisfy. So then the problem basically becomes, you know what this action should do on the level of cohomology, and then you actually want to find diffeomorphisms, right? Integrating this, right? You want an actual action. As it turns out, K3 surfaces have exactly something that allows you to do this. Okay. So K3 surfaces, I'll just go over the main things that we will use about them. So first of all, there's a universal family, and I'll go over the details of this in a bit, just outlining now. So there's a universal family over a concrete space. And using the Calabi-Yau theorem, you can put a Poisson structure on this universal family, right? And then in our final construction, these Poisson manifolds over RQ are going to be suitable restrictions of this family, right? So you're going to embed RQ into the base and then restrict this family. That will be the Poisson manifold you start with.
So this Poisson structure is regular, right?
Yes, it's regular. Yeah. Yeah, everything is regular here. I should have said that. Yeah. Yeah. So that's the first thing. That's how you get this Poisson manifold over RQ that you start with. And then for this action part, the crucial ingredient is going to be the Torelli theorem. So this like literally does what I just said we want. So this Torelli theorem says if you start with like an isomorphism of the degree 2 integral cohomology of K3 surfaces, satisfying some extra conditions, then there exists a biolomorphism between the K3 surfaces integrating this thing. So it does exactly what we want, right? Yeah, and then using this, you will get a Poisson action on this family. Okay. Now I didn't tell you what acts yet, but anyway, the Torelli theorem is the crucial ingredient to finding this action. So just quickly going over the stuff I just said. So what is a K3 surface? So a K3 surface is a one-connected compact complex surface with trivial canonical bundle. If you don't know a lot of complex geometry like me, then that's fine. Really, what you should know is the following. So basically, this trivial canonical bundle part basically will imply that on a K3 surface there is a like up to scalar multiplication, there's a unique non-vanishing holomorphic 2 form on it. All right, so this will come up later when we get into the moduli space. And then there are some facts that I will use. So every K3 surface is scalar. And also you can just compute the cohomology of these things. And what I'll do now is I'll fix a concrete model for this cohomology. I'll call it L. So that the degree 2 integral cohomology of a should be an X here. But the degree 2 integral cohomology is isomorphic to basically it's Z22, right? So 22 copies of Z with and the intersection form is the unique unimodular even one with signature 319. I mean, all this doesn't really matter. I'm just saying it, and I'm fixing here a specific model for it, right? So here this U is just 2 copies of Z with the hyperbolic form. So the matrix 0, 1, 1, 0, and then minus E8 is 8 copies of Z with and the intersection form is minus the E8 Cartan matrix. Right? So I'm just fixing this concrete model for the cohomology. Right, and then then we get, so I'm skipping a lot of stuff here in the interest of time, but so then we're going to consider this this thing, and this is the concrete space that I was talking about earlier. And what this turns out to be the moduli space of what you can call marked scalar K3 surfaces. Right? So what do I mean by a thing like this? What I mean is you take a K3 surface and you fix a marking. So you fix an isomorphism, or an isometry, I should say, between the cohomology and this L that I fixed, right? This concrete model that I fixed. So you fix a marking and you fix a Kähler structure. Okay, so you take K3 surfaces with a marking and a Kähler structure, and then this K omega 0 turns out to be the moduli space of these things. Okay, and then maybe I can say a little bit more about what's going on here. So really, the sigma here basically is going to like parameterize this holomorphic 2 form that I was talking about, right? Which is unique up to scalar multiplication. So that's why it's in the projectivized LC, right? And then the K is basically parameterizing the Kähler form. Okay, so that's the idea here. I mean, you don't really have to know what this all these conditions are or whatever. What matters is that this is really a concrete space, right? So basically, we're going to replace. So basically, our construction of our task of finding examples is basically going to be reduced to working with this space, right? And then all we have to do is like solve some equations relating to this space. That's the idea behind it. Right. So like I said, this is the moduli space of these things, these marked Kähler K3 surfaces. And then there's actually also a universal family over it. Right. So this is going to be a real analytic family whose fibers are basically going to naturally have the structure of these things. So what does that mean? It means that if you take the fiber over some K sigma, then it's a K3 surface, right? But there it has this extra structure. So there's a marking on it. So that's, like I said, this isometry between the cohomology and L. And then you also have a Kähler class on it. And in fact, the scalar class is going to be such that if you apply phi to it, this marking, you get mapped to K. Okay. And this is really nice, right? Because like I said, what we want is we want to start with a Poisson manifold over RQ, where we have this linear variation of the symplectic forms in cohomology. Well, what we have here is we have a universal family, and like I said, we're going to use later the Calabi-Yau theorem to put a Poisson structure on it. So what we then see is if you take a suitable embedding of RQ into this space, okay, can you hear me again? Okay, good. I know what happened there. So you can, what was I saying? Right, if you embed RQ into this K omega 0 in a suitable way, and then restrict your family to it, you will get a Poisson manifold. And then, like the way you choose your embedding of RQ into this, you can prescribe the cohomology classes of the symplectic forms on the leaves, right? Because you can use these markings to like read off the Kähler class on the fiber by just data of the base, right? So that's going to be the idea, right? Right. So that's the family. And then, like I said, you can use the Calabi-Yau theorem to put a regular Poisson structure on Ku. So in such a way that the symplectic leaves are just the fibers, and the forms are the Kähler form associated to the unique Ricci-flat Kähler metric on X, whose Kähler class is the one that you have on it, right? So then you actually have a Poisson structure on this. And then to get this action, well, so the group that's going to be acting here naturally is the group of isometries of L, of the lattice L. And of course, there's an obvious action of this OL on K omega 0, right? K omega 0 was a space in terms of L, and all the conditions were in terms of the intersection form on it. So group of isometries will act there. And then the Torelli theorem will imply that this action on K omega 0 lifts to a Poisson action on Ku. Okay, so this takes care of that big problem in the construction. Yeah. Right. So let me now rephrase this this construction purely in terms of this setup. I sort of mentioned this before already, that now all we need to do is find suitable embeddings of RQ into this K omega 0. And of course, you need to find a subgroup of OL that acts in the way that you want. That's what it's come down to now. Right, so like I said, you're going to take an embedding of RQ into K omega 0, and then you want the first component, so the LR component, to have this form, this linear variation, right? Because like I said, this LR component of K omega 0 is governing now the classes of the symplectic forms we have on the leaves, right? So if you assume that the first component of F has this form, where these are elements of L and these are linearly independent, then once you restrict this family Ku to RQ, you will automatically have this linear variation that we want, okay? Right, and then we need to have a subgroup of OL acting in the right way. So what do we want? Well, of course, first of all, we want the action on K omega 0 to preserve the image of F, right? So we get an induced action on RQ. And then we want the action on RQ to be free, proper, and by integral fine maps, right? Such that the quotient is compact. Yeah, and then from our setup, we will see that if we take the restriction of Ku to RQ and then quotienting by this gamma, then we get a PMSCT whose leaf space is this B, right? This quotient. Okay. This is basically just a different way of stating this general result that Martinez Torres had in his original example. Right, and now so basically everything has been reduced to like finding this suitable data, right? So then you just need to find the correct ones, right? So that's what I'll do now. So yeah, so first I'm going to recall this original example that will yield a PMSCT with leaf space S1, and then go to the examples for the tori. Right, so there's a classification of integral fine structures on two tori, and then it turns out that the strongly integrable affine ones are the following. So you just have the standard one, which I'm singling out because the construction will be a bit different for it. So this is just the standard action of Z2 on R2. And then you have these non-standard ones, where basically you have this term here, this x plus ny, where n is a positive non-zero integer. And then you can also vary how much you translate. And it turns out that all these are non-isomorphic, right? So this is these are all of them. All the different strongly integral affine structures. Right. So then before I get into the examples, I need to establish some notation. So recall that this L, this consists of 3 copies of U and then some E8s. So I'm just fixing some notation for the standard basis of the copies of U, the 3 copies of U that are in L. And then I need, this doesn't really matter, but so you basically need to find some suitable vector in minus E8, which has some properties. And then you consider A and B to be this vector sitting in either the first or the second copy of minus E8 in L. Okay. This is just to make the embedding work, basically. Right. So then for this PMCT with leaf space S1, you consider the following. So this is the embedding you use. So as you can see, this first component has the form we want, right? So we just want to embed R now, and then we just have some element of L plus some non-zero element of L, right? That's all we need here. So this makes sure this is says that the linear variation is satisfied. And then this second part is basically just making sure that you actually land in K omega 0, right? So, and this is where basically this part, I guess you can say, is inspired by this Kochik construction, right? So that's where the intuition for this comes from, I should say. Right, and then to get the action, in this case, we just want Z to be acting, right? So we just need to specify an isometry, and it's just this one. There's not really much going on here. You can check that this has the right form, like the right induced action. The induced action on R here is just the standard one by translation. Yeah, so this is how it acts. And this will, if you plug this data into the construction, you get a PMSCT with leaf space S1. Right, so then for the leaf space T2 with the standard integral affine structure, sort of an obvious generalization of this. Basically, because you have more room, like there's a third copy of U in there, which has this T, so you can sort of do this a similar thing. So you're just taking this embedding, and now for the action, you need to specify just 2 isometries. So the first one is the same as what you had for S1, and then psi is sort of the same thing, except taking like the first 2 copies of U, you take the first and the third, right? And you can check that this, again, does everything you want. So then this will give you a PMSCT with the standard integral affine 2 torus. And then for this last example, this is where the non-standard stuff comes in, and this is where stuff gets a little bit more complicated. So the first component is actually the same here. But then you're going to have to change up your actions, right? So your isometries change. Now, the first one is sort of the same, where instead of translating by 1, you translate by P, right? And then the second map, you need to do some extra stuff to make it work. And then consequently, the second component of this embedding is also going to have this different form. So this is not very insightful, I know, but I feel like I should just write down the formulas. And this is so this works for any P, N, and Q. And so you get a PMSCT for all these other strongly integral affine 2 tori with the as its leaf space. Yeah, so that's basically what I what I wanted to say.